Okay, before I start my lecture today, just to let you know that homework assignment number 1 will be due this Friday. So what I plan to do for those of you who need some more information about the homework, so I would like to use today's office hour, which means that we'll finish at 3 o'clock. I'm planning to do maybe starting at 4 o'clock. I will have a office hour for you to ask any question, how to take care of homework assignment number 1. Okay. So the other thing is I announced on the Facebook. I haven't announced on. Sorry, let me just get this one off. I cannot do that. Hold on. Why? Yeah, I announced on the Facebook regarding the dates for midterm 1 and midterm 2. So both midterm will be open book, open internet, and you just cannot communicate with another person. So because midterm 1 is going to do online, so what we need to do is have everybody be on Zoom. And for that period of time, for that 1 hour and 20 minutes, I will need you to, how do I say that? Turn on your video. You don't have to turn on your audio, but at least you turn on your video. Okay, at least I know you're there. Not somebody else is doing your. And I will basically at the end of the midterm, you will email the file. You will receive an electronic file. You're going to email that file back to me around that period of time, so I know you turn in your exam. Okay. By the way, I haven't done this very much, so okay. Yeah, I must mistake. Okay, did I say 21? Okay, I'm sorry. I read it wrong. Okay, it's 21. If I say so, that's January 21. Sorry about that. I must have thought it was this Friday. Okay, so you have extra time. That's fine. Thank you for letting me know. Okay. All right, so we're going to continue on the first set of lecture on the files. So the previous 2 lecture, we talk about the idea of I know. And if you ask me what is I know is essentially 15 pointer to allow us to be able to represent a large file, and also we will be able to access the file very efficiently. On the other hand, there are other properties about I know, which I will talk about later, especially try to deal with robustness of the file, recovery of the file. In fact, I know is actually very well data structure. I can actually do something such as what we call background FSCK, file system integrity check. Is actually based on I know. So we will see this picture again, but at this moment, I hope you understand this is the I know data structure. So I just want to review what we did so far. I'm going to skip this about this portion. I'm going to move this here. Okay, so I basically say the file system have a few property I would like to maintain. For example, it will need to be hierarchical, which we will talk about how do you represent a hierarchical directory together with I know. That's why we call directory block and I know block. That's why this two will go hand in hand to put the whole thing together. In fact, everything code in a typical Unix operating system to deal with I know is under this subblock called FFS, fast file system. But anything to do with directory is under the code of a UFS, Unix file system. So sometimes you see UFS, FFS, they're usually responding to this part of the function. So, and the other thing is very important, which we haven't talked about is the robustness against all sorts of failure. So that's why later we're going to talk about is we only talk about inode. The next topic we're going to talk about is directory. And then we're going to talk about this robustness feature such as soft update, FSCK, and snapshot. This three I call is a trio because this three property, they each have their function to handle the robustness of the file system against different kind of failure. But these three, they must work together. That's kind of the magic part about Unix file system. There are three different concepts, but they have to work together. If you're missing one, then all three will not work correctly. By the way, that's the same thing. Soft update, FSCK, and what I call a snapshot. Okay, and this three concepts together has influenced many modern file systems, such as Mac OS. They're basically along the line that we developed the Unix file system here. And the other thing, which is the file system, is about extensibility, that you can make the file system more flexible and introduce new functionality. And that's the concept called vnode. So you have a directory, inode, the trio, which is soft update, FSCK, snapshot, and then vnode. Those are the things, pretty much basic file system that you should all understand. And this is essentially this 1, 2, 3, 4 different concepts are going to be the main thing I'm going to ask you for homework for your midterm number 1. Okay. And I just want to add, I usually want to challenge students to think about, well, I mean, we already know this I said we already know means that we already developed this concept. We're already using this concept for a long time. But the thing is that we actually we should always think about some kind of disrupt idea, means that there's other ways I would like to structure, and I would like to be able to find my file. I just want to tell you that I know it's nice if you know your file name, or if you know the file is under certain directory, which is great. But the thing is that there are other ways we can structure our file. I mean, here I give an example. I mean, there are some file, for example, I'm actually, for this period of time, I work on a project with, say, 3 of the team member. We have a team of 4 projects that we actually edit PowerPoint file, we add the source code, and we do a lot of things. So there are basically a bunch of files, a group of us are actually using during this time. So, but the thing is that instead for me to put all this file in a single place, which might be hard because we typically want to move the file under different folder, even create a symbolic link, it could be a trouble when you want to handle a group of file accessed by a group of social network in some sense. And therefore, it's always interesting, can I actually structure the file differently such that I can search the file based on some kind of social relationship? For example, I can actually just say, instead of knowing the directory about where it is, I actually can say, hey, I and John and Mary and Greg, we actually work on that 6 years ago together for about 2 months, ECS 251. Can you actually find me all the file that we actually modified during that particular 3 months? And that will be a search mechanism that not only look for time, but looking at who are involved in those period of time. So the thing is that when we think about the traditional file system, we always think about maybe there's other ways we can structure the file. That's how we can actually keep moving forward. Okay. All right. So now I'm actually going to talk about the rest of the topic. The first topic I'm going to talk about is the directory. So I already showed this picture earlier, but now I'm actually going to a little bit detail. So you can see that this is a hard disk. I have a different partition. And one of the partition, I actually have a boot block. I have a super block. And then I have the rest of the block, which is I call the inode block pointer block, which is indirect block. And I have a directory block, I have a data block. So essentially, let me actually show you this picture, and then we're going to see the examples. You know the meaning of each of this arrow. Okay, so essentially this works this way. If you have a directory block, the directory block is essentially contain a lot of pointer to first the file name and the inode. And then from there, you actually point to one of the inode. And from the inode has all the pointer to the data block, some of that actually to the pointer block. But basically, directory is a place that's actually hosting the file. Okay, there is one thing I should actually tell you. This is interesting. I should have asked you earlier, but now I want to go back to the code. Remember I showed you this piece of code. Oh, sorry, this is UFS2, I know. I know some of you actually teach me how to do this. You know what? Give me a second. I'm going to do this. I make the mistake. I'm going to print it into a PDF. Oh, can I print it with color? Sorry about that. I want to print it with a color. Okay. Yeah, I'm going to save it. I'm going to save it desktop. Give me 1 second. Okay, so while I'm actually waiting for my PDF, if you look at this data structure, this data structure represents inode. And I say inode represent a file. This is essentially all the information about a file. So my question to you is that have you found any place in this piece of code it's about file name? Let me actually now try to use the PDF version here. Okay. Put it down here, and then I'm going to do view. Where is the slideshow? Okay, good. All right, now I'm happy. So this piece of code we're talking about, where in this inode definition that you see file name? Let me stop sharing. I just want to ask all of you, is file name the name of the file associated with inode? That's my question. Let me see if some of you might actually already chat. Okay, can you hear me now? Did I lost everybody?
Professor, now we can hear you, but your video and audio is breaking.
Okay, thank you. Okay, let me repeat. Sorry about that. Oh, okay. I need to share my screen again. Okay, so this is the code for, wait a minute. How do I, did I, okay, yeah. Okay, so this is a piece of code that's actually deal with UFS2 I know. And I just want you to take a look at this code about all the data structure, all the attribute that associated with file, because I said I know represent a file. Every single file you have, you must have one I know associated with that. So my question to all of you is, have you found an attribute that's represent the name of the file?
Is it line 127?
Line 127, no, that's an integer called di nlink. We're actually going to talk about nlink. This represent the, there was a concept called hard link in Unix file system. It's a little bit different than a symbolic link. So in a typical window file system, you have something called shortcut. Shortcut is a technical term we call symbolic link, but this nlink is for something we call hard link. No. So the answer to my own question is that there is no such thing of a file name in a file. So essentially, a name of the file is not part of the file. That's kind of interesting. Some of you will think, oh, when you create a file, you must have a name for this file. But it's very interesting if you look at the file system design, the file is really about the sequence of bytes. And then we actually using a data structure called I know to pointing to those sequence of file, the file blocks. And that's it. If you take a look at that, there is a SS mode that's it's there. User ID, group ID means that who actually create this file, who can access the file, the block size, and also there are 3 timer, means that when is the last time you read a file, when was the last time you actually modify the file, when is the time you actually modify the I know of the file. And so you can actually see there's a lot of timestamp. And then you have other flags that will be related to the file. But there is nowhere in the I know itself, it has the file name. So which means that when I now, that's the reason I want to go over here. Hold on 1 second. I want to go to this data structure. So in this picture, when we have an I know, which is represent the file pointing over there. And the thing is that there is nothing about the file name itself. The name of the file is actually there. And therefore, everything about the name must be in somewhere else. And you can guess where is that somewhere else? Is actually the directory. So the directory is actually a place that will store one or more what we call directory entry or direct. So I'm going to show you what the directory entry looks like. Wait a minute, do I have the code for directory entry? No, I missed that. I'll show you later. Okay, so here is the directory called direct. So in the directory entry, you actually put the name. And then you have only 2 parameters for each of the entry. One is the name of the file and also the I know of the file. So with the name and the I know, then I can actually mix these 2 together. Any question about this concept? I'm going to show you the code. You will see exactly what the directory entry looks like, okay? All right, I'm going to move forward to this part. Okay, so here is the directory entry looks like. So you can see this is data structure, struct duran. It has two parameters. One is the inode number, which is you're going to do that, you're going to access that. And the other one is the dname, which is the directory name, which is the name of the file over there. So let's actually conceptually look at what is the directory looks like. So a directory is actually also a block, which what we call a directory block. And inside the directory block that you have a multiple duran, directory entry, and each of the directory entry is contain the inode number and the name you want to associate to the inode in this directory. So essentially this one, this example, I have a 3 directory entry, and one of them, this inode is actually pointing to those data block or indirect block that's actually from this inode here. Okay, so that's the typical size of the directory. Okay, based on this, now we're going to see a example about very simple file system. By the way, I want to pause a little bit. This is keep blocking the view. Are there any questions you would like to ask me at this moment about the concept of directory entry?
Yes, Professor, I have a question.
Okay, good. Go ahead.
So is a directory entry structurally any different from a file or inode? Like structurally, it seems like the same thing. It's pointing to some other data blocks, which again point to different data blocks, but again, unless I'm wrong.
So directory entry, when they have the inode, it's not a pointer to inode. It's just an inode number. That inode number is sufficient for the operating system to go through the file system to look at which inode correspond to this file. So for example, when I look at this file system, right, you can see that from the directory entry, there is inode number. And remember, I have an ilist. When I put all the inode together, means that I actually have inode with all the index. So the first inode is inode 0. And then inode 1, inode 2, inode 3, things like that. So that's why I have all the inode already indexed by some number. So that particular inode number will enable me to find out where is the inode I'm looking for in this directory. Okay, it's like a pointer, but it's actually sorted out by inode itself. Okay. Does that somewhat answer your question?
Yes.
Okay, so let me show you this example. This example will give you a pretty clear idea about how inode and the directory are working together. So you can see that here we have a very small file hierarchy. So you have the root file system, and then you have another directory is number 4, which is /usr. So you can see this is a root. /usr is actually going to be here, and /foo is going to be another file or directory. And then you have another file called vn-unix, which is /vn-unix come to over here. So you have a file hierarchy looks like this: /usr foo, /usr bin, ex or graph, and things like that. So we're going to represent this using the this block, using the inode block and directory block, so you can actually see what's going on. So the block looks like this. Okay, by the way, over here, let me see if I can minimize this because it's actually blocking the view. Okay, sorry, I have to put it here. Okay. Okay, can you see my screen? All right. Okay, so on this side, on the left-hand side, everything is what we call inode block. This is inode. You can see inode number 2, inode number 3, inode number 4, inode number 5. It basically has that 256 bytes. It's just all on the inode list. Okay, so it's compared to this one, we're talking about, remember, this is inode number 2, inode number 4, inode number 5, inode 6, 7, 9, 10, right? So over here, you have all the inode. 2, 4, 5, 6, 7, 9, 10, whatever. That's the inode block. On the right-hand side is what we call directory block. So now we are going to see how the inode block is actually going to the directory block. By the way, there is a magic about inode number 2. So in any Unix file system, inode number 2 is the root of the file system. So if you take a look at this one is always the beginning of all the file. It's the root of the file system. The root of a file system is always inode number 2. So you will say, well, where is inode number 0, inode number 1? So just to let you know, inode number 0, inode number 2 is currently unused. But historically, it was used for some other special purpose. Therefore, 0, 1 were reserved. And when you're going to start to search a file system, you always start with inode number 2. That's why it's a convention. So when you open a hard disk partition, and then you actually know after the super block and the boot block, it will be inode block. And then look at the inode list, you know the inode number 2 is going to be the beginning of the file system. Because it's very important, because when you don't have anything else, you start to search for the information. For example, you want to search /usr foo. You need to know where's the root, because only from the root you can actually build your path to access to other file. And where you started with the root, inode number 2. Okay, just remember inode number 2 in Unix file system represent the root. Okay, so now you have a root. And from the root, because the root is a directory, so it's actually going to pointing to a directory block. So you can see that this directory block has a 4 entry. The first column represents the name of each of the entry. The second column represents the inode of that entry is pointing to. So now let's actually go back to the previous slide. So over here, you see this is a root. Root actually have a 4 entry. One entry is dot. Another entry is dot dot. I hope you know Unix file system. Dot means the current directory. Dot dot means the parent directory. Because this is a root, the parent is himself. And then there is another directory entry is a VN Unix. Another directory entry is user, USR. So that's why we're actually looking at this picture. The root is inode number 2. And this inode is actually pointing to a directory block. It's not a regular file, it's a directory file. And then it has 4 entry. One is, the first one is just a name, those 4 entry. And then there's inode number, because remember the dot 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 point to itself. So that's why the inode number is 2. And USR, let's actually go to USR. USR is actually inode number 4. Oh, great. Now I'm going to move back to the left side to find out number 4 is the inode for that directory block /USR. And over here, /USR, again, it has 4 entry, dot, 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 bin, and foo. So now I actually, for example, I look for bin. Bin is inode number 7. So now I go to inode number 7. And from inode number 7, I actually see, okay, this is still a directory. I'm actually having another directory block, which is a /USR bin, which has dot, 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 and then has ex, graph, and vi. So now it's a little bit complicated. So I want to just go back to the picture to remind you that this is the picture we're talking about, number 7, which has a 5, which is ... the parent directory 4, and ... to pointing to itself. And then the graph point to executable of graph, which is inode number 10. And then now this is interesting. This is what we call hard link. Means that I could have a 2 directory entry, different name, but they are pointing to the same inode. So that's why you have vi and ex. So now if you go back, oh, sorry, go this way. Now you see that they have ex and vi. They're 2 different names, and then they're pointing to the same inode, which is the same file. So that's basically we're saying that, okay, there are 2 things we should know. Number 1, you should know the name of a Unix file system. It's always associated with directory, not with the file itself. This gives us the flexibility that such that we can actually have a multiple name of the same file. We can have a multiple name because now in this case, this executable here, which represented by inode number 9, it actually has 2 names. One is ex, one is vi. They both actually pointing to that. Okay, so that's number 1. Number 2 is about the attribute we call unlinks earlier. If you remember, I show you the UFS2 inode. It has an attribute called unlinks. Let me actually just go back to give you a very quick picture about what I was talking about. Okay, over here, this is UFS2 inode. You actually see there is an attribute called unlinks. This is called file link count. In the case of that directory /usr bin, that inode, the nlink, sorry, not USR, the inode number 9. The inode number 9 is a file. Remember, it has 2 names. One is ex, one is vi. Because it has 2 names into that, meaning that there are 2 entries in the directory block is pointing at this particular inode. And that therefore the din link for that particular file is going to be 2. Okay, let me just go back to over here. Now you need to take a look at this very quickly. Let me use this picture to say what I just say again. This is a file which is represent inode number 9. And in the whole file system, it doesn't have to be from the same directory. By the way, it just happened to be this case, both vi and ex, they're actually from the same directory block represented by inode number 7. But it could be the ex could be from 5 or from the other place. As long as you have 2 directory entry, they're with the same name or different name, doesn't matter. If they actually pointing to the same inode, this inode, the n link is going to be 2. If there are 3, they're going to be 3. There are 5, they're going to be 5. 200, they're going to be 200. So that's actually called an n link, number of links pointing to this particular inode, number 9, which is this one. Which is this one. This is inode number 9 because ex and vi, they both pointing to inode number 9. So over here, the unlinked data for inode number 9 over here is going to be 2. Okay, any question about this picture about how inode block and directory block, they're actually going to working together? And the second question is that the meaning of n links, which is the hard links to a particular inode. Any question? Let me actually.
Oh, sorry. You can go ahead.
Yeah, go ahead, please.
Professor, do the file inodes and the directory inodes sit to where do they sit in the file system? Do they sit at the beginning, like how you have shown? I mean, do they sit together, or is there a logical separation to the storage?
Which part of the information?
The directory inodes and the file inodes.
Okay, the directory inode and file inode, they can be sitting any place. That's okay. But the inode block themselves, the inode usually need to come the first part, because the reason is that I have to start to look for file. I have to look for inode number 2. So I need to have a pointer. If you want to put inode block also scatter around, then you need to put some information in the super block or boot block, so they will know where to find the first inode, which is the root. So that is not completely strict, but the earlier design of the Unix file system, they all put their inode in the first portion of the hard disk.
Got it. So just to confirm, uh, the contents of the directory inode is same as the contents of the file inode, the structure that you showed?
No, directory inode is very different from the, oh, okay, directory inode, yes, is exactly the same. Yeah. Yeah, directory inode is exactly the same, 256 bytes. Yeah, they're the same.
Thank you, Professor.
You're welcome. So there is a question about, let me see. Looks like a symbolic link or hard link. Yes, I think this is a question by Guisan and Mithreya that on the chat. It is, you are right, that your observation is right, that the 2 connection to the inode number 9 is actually the hard link. It is hard link actually. It's not a symbolic link, which I will talk about the difference between symbolic link and the hard link later. Okay. Okay.
Professor, just a quick question. So in order to compute the actual size of the hard disk held by the files, do we need to go through the entire directory structure and then compute it?
I will address that question a little bit later. All right, that's kind of talk about a different question. There's a way to do that much more efficiently, but I reminds me to ask the question again. But I actually want to ask you a question, okay? All of you question related to what I think is Aaron Dan asked when the count becomes 0. Okay, I want to ask you a question, is that what do you think is the usefulness about this attribute called unlinks? Let me actually share the screen again, and you can. Oh, I haven't shared the screen. Sorry about that. Hold on. Always forgot to share the screen. Okay. Okay, so we see this picture here. There is an attribute called DIN links, which represent how many pointer from all the directory block to this particular inode. So why is this information useful? Why do I actually need to remember this number?
Sometimes you may want to delete a file and you want to remember how many other files or directories point out to this before removing it completely from the memory.
Exactly. That is actually the question Aaron Dame asking, is that what will happen when the count of the DIN links go to 0? If this count goes to 0, that means there's no longer in the file system that's actually any directory entry is actually interested in this file. So whenever the DIN links goes to 0, we're going to remove the file. We're going to remove the file, right? If the DIN link is actually go to 0, that means nobody is interested in this file anymore. So for example, let me actually go back to this particular data structure. So let's actually see what's happening. So the first time, let me see. Okay, so the first time somebody remove, say somebody remove VI /USR bin VI, somebody remove that. When you remove that, the DIN link is going to decrement from 2 to 1. It's still not 0. But the second time somebody removed EX, when somebody removed the EX, I'm actually realized that the DIN link is going to 0 from 2 to 1 and then to 0. So which means that there's nobody in the whole file system directory is interested in this inode anymore. So therefore, I'm going to remove this particular file that's represented by inode number 9. Does that address your question, Arindan? Okay. Is there any question? Okay. Now I'm actually going to ask you a question. We will see this a lot, but I'm going to ask you this question anyway. What do we mean by removing a file? I'm going to ask all of you. When I say, okay, this inode 0, sorry, this particular inode, the nlinks value goes to 0. We're going to remove the file. I just say we're going to remove the file. But what does that mean to remove a file? When I say ask this question, I'm asking what part of the hard disk I need to remove certain block of information. What kind of blocks I need to touch or modify or remove in order to remove a particular file represented by inode number 9. What kind of things I need to remove? Okay.
We don't need to remove, but we can reuse it for something else because
we can reusing for something else, but we need to remember which one is free, right? We have to remove that. So in fact, removing a file is not trivial at all. I mean, in fact, I think it's much harder than you add something. When you remove, it's actually pretty tricky. Let me actually tell you what kind of thing you need to remove. You need to remove the inode block, or at least make the inode block become free so people can use. You need to remove or modify the directory block because that particular file is no longer there. You need to get rid of that, right? And you need to remove what we call free blocks, Bitmap. There are actually 2 Bitmap represent each of the block and each of the inode is free or not. That's called free block Bitmap and free inode Bitmap. So there are 2 Bitmap represent whether this particular block is 0 or 1, is actually in use or is a free. So you can see that there is a lots of data structure that you need to remove. At least I mentioned already 4 different data structure: inode block, directory block, and then free block Bitmap and free inode Bitmap. So I have a 4 different structure I need to modify before I can consider a file to really remove from my system. It's not about whether you can recover, it's just remove it from the simplest scenario from my directory. Does that make sense to you? All 4 of them? Okay, then I'm going to ask you a follow-up question. When you try to remove this, but in the middle of removing this 4 different type of data structure, your system crash. Your system crash means that somebody just kicked the power cord and suddenly your machine got shut down in the middle of removing this 4. Now the question is, when you turn on the machine, are you sure that your file system is actually still consistent or the integrity is still good? Do you think that this is important? Because how often we forget to actually charge our battery or to just because of the power outage or because whatever other reason, and suddenly our system shut down unexpectedly. And then we're in the middle of modify different structure of our file system. Some of this is inode, some of this is directory, some of maybe pointer block, and some of this is a bitmap. And then all of this information is in the middle of being modified, and suddenly it's gone. And we have to actually, when you reboot the system, we're actually not sure that the file system, what's the status. In fact, is the part of the lecture I'm leading to next is actually going to show you the design of a Unix file system that's actually, regardless how you actually crash, we guarantee the file system is actually still consistent and with integrity. And in fact, that is a very interesting part of the, in fact, I feel that the most exciting part about this sequence of the lecture is this part. I mean, how do you actually design a system, regardless when it crashes, how it crashes? I can still guarantee the file system is usable, is nothing corrupted, and I can continue to actually develop whatever I'm developing, okay? Any question before I start talk about the trio? So I'm actually already told you about inode directory block. Now I want to move into the trio, which is the soft update, background FSCK, and the snapshot. Any question?
Sir, I have a question.
Sure, go ahead.
In the directory inode block, the D name, is it the relative path or the absolute path?
The D name in the directory part is relative. It's not just relative, but it's only one single name. So it doesn't have like a slash something or dot dot slash something. It's basically just the one single segment of the name. Yeah.
Okay.
And I will explain the difference between symbolic link and hard link. With symbolic link, yeah, you give the whole full pass or relative pass, whatever. That's symbolic. But yeah, hard link is a little bit different. Any other question? Okay. You know what? I don't think I need this anymore. This part, I don't have the code. I can use I'm going to use my PowerPoint again. Okay, so we're done with this picture, and then this picture, you kind of know what's going on. And this is essentially just representing the structure between these two, and then there's end links. And I hope now you understand how this picture lay out. Okay, your file system. Remember, inode number 2 is actually represent the root of the file system. Okay, so I'm actually going to skip this question. This is the two different way of specify whether it's a hard link or it's a symbolic link, but I'm actually going to coming back this later. I'm going to skip this inode stuff. And no, I'm actually going to stop this. Okay, so I'm actually going to talk about the first concept of this three is called snapshot of the file system. All right, so what is a snapshot of a file system? So essentially you can think about it's like a time machine. I mean, for those of you using Mac, you probably use time machine. So time machine is a way for you to be able to capture a particular snapshot about the file system you're in. And then you actually try to provide a backup, and then so if something goes wrong, you can actually go back, right? So essentially, a snapshot is trying to dump reliably an active file system. So it means that you're still using the file system. Remember, we always consider people are still using the file system, and then how do we actually be able to do a snapshot of the file system? And the third thing is that the snapshot of the file system is actually very useful for supporting the other trio. It's called background FSCK. Okay, we're going to talk about that. But first, let's worry about what is a snapshot. Okay, so when you look at this slide, I must make this slide long time ago because I said, what will we do to dump our 40 gigabyte file system? I mean, today's file system is hardly 40 gigabytes. It's probably going to be 4 terabyte, this kind of space. Okay, so how do we actually be able to do a really large hard disk to do a snapshot? And yet we can actually do it when you're actively using a system. So let me ask you a question. If I want to do a snapshot of a 2 terabyte, let's use 2 terabyte, 2 terabyte hard drive. If I'm doing a snapshot, how long do you think it will take for me to do the snapshot? Just 2 terabyte. How long? Anybody?
I think maybe we only need to capture the inodes and directory blocks, maybe not the entire disk.
How long it will take, do you think? You're touching something that's actually related to what I'm going to show you, the solution, how we do that, but not exactly. But I just want you to figure out the key thing is how long do you think it will take for us to dump a file system, to take a snapshot for the first time?
Depends on the maximum number of inodes and directory blocks supported by the system.
Okay, so how about 5 minutes? 1 minute?
Maybe a few hours, 2 hours.
Actually, the answer is a few seconds. It's interesting, it's a few seconds because it's related to inode, but I'm actually using the inode somewhat differently. So let me actually take a look at this. What is inode? The inode looks like, the snapshot looks like this. I'm actually going to take what I call a conceptual, snapshot. So what is a conceptual snapshot? Is actually I freeze all the activity about the file system. I'm talking about conceptual, okay? Nobody touched the hard disk or the partition of the hard disk. And then I actually copy the whole thing to another space, right? And then I let you continue to use the file system. And the thing is that I actually can play a little bit trick and such that regardless how big your file system is, I can probably do it less than a quarter of a second. I can do that, okay? And what the trick is this. So I want to do this to make the hard disk into the other space, and such that I can actually be able to do a snapshot over here. But what I really are doing is this. Okay, I should actually tell you this. So after you take the snapshot, and now you start to modify your file system, right? So now you have 2 different conceptual image about your hard disk. One represent the snapshot you took at that time, and one represent the current active file system. So this is actually what we want. But the concept is we actually using the concept called copy on write. I don't know, let me ask you, have you ever heard about the term copy on write in computer science? Copy on write. Anybody? I didn't look at the chat, so you need to speak up.
I think it comes up in databases.
Okay, so what do you think is the concept of copy on write? What do you think the copy on write? Can somebody describe the concept copy on write? Yeah,
just update the stale copy of, just update the stale image of the hard disk that we have already kept.
Okay, so let me actually tell you that this is my version of describing the concept. The concept of copy on write is that I actually avoid the real copy until at the point that the data I'm supposed to copy earlier is going to be expired, is going to be overwritten. So in the case of the red, so before you have the red, it was a blue, right? So when it was a blue, I'm supposed to make the copy to the snapshot. But I decide I'm going to do copy on write, means that I'm actually going to avoid doing the copy. I'm not going to copy that file. But until that this particular data is going to be overwritten, somebody is going to overwrite, like this situation. So only at that time, I will make a copy. So essentially, if you have an active file system, if 99% of your file you never modify, then I'm not going to do any copy. So that's kind of the a principle in not just operating system, but in programming language, in distributed system, in database. We all use this concept called copy on write. Essentially, it's a lazy fashion of doing the copying. So only do the copy when you're going to about to write on the data I supposed to copy earlier. Okay, so is that clear, the concept, copy on write? So that, go ahead, please.
What if the system shuts down, or what if the system loses power before we copy? Isn't all the data lost?
We will look at that. Okay, remember I said there are three things: copy on write, sorry, not copy, background FSCK, snapshot, and soft update, right? So if you have all three, then that's not going to be a problem. I'll explain to you. But remember this question. This will be an excellent question for us to examine that we're going to see for the other two part of the trio. Okay. Excellent question. Any other question about copy on write?
Professor, I had two questions.
Sure.
Suppose that you are not doing any snapshot for some time, and then you start doing snapshots. So basically what you have done is you like the first time when you perform a snapshot, there has to be copies, right?
Well, the thing is that there is a copy, yeah, but I only need to remember you. Okay, let me actually tell you, answer your question this way, is that when I take a snapshot based on the copy on write principle, I only need to remember whether this particular block has been copied or not. If this block has been copied already, then when you write on it, I don't need to worry about that. But if this particular file has not been copied since I took the snapshot, then at the time when you want to overwrite to that particular position, I'm going to do the copy at that time. Is that, do you understand what I'm saying?
Yeah, I do get that. I do have a follow-up question.
Sure.
Where is this whole copy being stored?
Okay, that's a good question. We're going to find free block. We're going to find free block, and you will actually see how I do that with I know. In fact, the whole snapshot is represented with one big I know. So why don't we actually move on to the next question, okay?
Here, thank you.
So here, this is actually what we call a snapshot. A snapshot is actually a file. And now you see that it's also I know. The I know has a 15 pointer, right? And then it has single interaction, double interaction, right? So let me actually tell you that the snapshot is a I know. But instead of when you actually create a snapshot, instead of saying that what is the pointer pointing to this block, when you create a snapshot, you actually only put two labels. One label saying that this particular block is not copied, or this particular block is not used. So what do I mean by not copy and not used? I'm actually going to skip this part, because this part actually talk about the snapshot itself. I want to use this as a picture to tell you this. So this is a snapshot I know. Over here, this is the hard disk, or this is the file system. I try to do a snapshot. So you can see that under here, the snapshot, there is a certain number of blocks, like the yellow block, they're being used. They're being used means that it actually represents either a idle block, directory block, indirect block, or data block. So the yellow are all the blocks that are being used. And the gray color represent those blocks are free, means that they're not being used. Okay, it's there. So when I take a snapshot, what I really need to do is that I am actually go through what we call free block bitmap. Remember, I have a data structure called free blocks bitmap, which represent for each of the block I have in my file system, I have a 1 bit to represent it's a 0 or 1 to represent whether this block is being used or not being used. So what I did is I go through each of the bitmap, which is the different structure on the file system. And if that bitmap says for this particular block is actually free, then I'm going to put a not used. If that block is happen to be used, then it's a 0. Then I'm going to put another text say is not yet copied. So over here is either the triangle represents a free block, or is not triangle represent it is actually a currently being used block, which means that I not yet copied. Okay, so let me actually tell you the other very important concept, which you might or might not get it at this point. Remember, this is I know this is my first 15 pointer, right? Sorry, first 12 pointer. This pointer is actually correspond to the first block. So I'm actually aligning each of the disk block in my file system. I try to do snapshot corresponding to each of the I know pointer in this direct, single, double, triple interaction. So the last block in my hard disk is actually correspond to this particular pointer here, for example. And the thing is that if it's a triangle, you put a 0 there, it might be represent not used. Okay, so that's why 0 and 1 represent. You know what? I actually realized that why remember I said the root of the file system is I know number 2, right? The root of the file system is I know number 2. And therefore, wait a minute, maybe this is wrong. I'm just saying that 0 and 1, because 0 and 1 is never used. So 0 and 1, I can use that 1 represent not used, 1 represent not yet copied. I have to check exactly how do I actually represent this information here. But what I'm saying is that each of the pointer here now no longer represent the pointer. It's actually represent whether that particular disk block is not used or not yet copied. Not used means that it's basically a free block. Not yet copy is that it is not a free block. I haven't done the copy. Okay, so now I'm actually going to see how when you actually later. So this is the time when you actually take the snapshot. So now assuming I actually make a change to a particular block. Say I want to make a change. I want to modify this 2 block. Okay, assuming I want to modify this 2 block. So how do I actually handle that? Now I need to do the copy because copy on write. I need to do the copy. So somebody want to modify this 2. So what I need to do is I need to actually first copy the content over here and then allow you to actually modify this block. But I actually keep the pointer about the new block you actually just copy. And then now you're actually really putting the pointer over here. So the pointer is going to point to this one. So after, so this is a before, this is after. So after that, you make a copy, and then your snapshot inode will remember where it is. So now your snapshot inode has three types of information. The first type of information is not used. The second type of information is not yet copied. The third type of information is those real block pointer that you actually make a copy and where they are to represent this. So then this data structure preserve what you have as a file system, as its content when you take the snapshot. Any question?
Question, Professor.
Sure.
So I'm still a bit confused. So when you're taking a snapshot, are you taking a map of the file system itself in that inode, or are you just like storing the pointers to different inodes themselves?
Okay, this is exactly what I will be doing when I create a snapshot. When I create a snapshot, I just read the free block bitmap. Okay, let me actually write it down because I use this term a lot, but I never put it there. There's something called free block bitmap. So free block bitmap is a binary array represent the status of every single, sorry, let me actually just click this. Let me move this here. So free block bitmap is a data structure contained in the file system to remember for each of the disk block, whether they are free or not. So what I did when I take the snapshot is that I just go through this bitmap, the binary array, and check one by one. The first bit, if the first bit is a 0, that means this block is not free. Then I'm going to put not yet copy. If I actually find the second bitmap is actually 1, means it's a free, then I'm going to do not used. So essentially, when I create a snapshot at the time is I just need to read the whole free block bitmap and then polish them into this gigantic, what I call snapshot inode, and write the value either is not used or not yet copied, like this. Okay, so I just need to write either not used or not yet copied into each of this entry, which corresponding to each of the block in my hard disk. Does that make sense?
It does. A follow-up question on that then. So if you're storing like the snapshot in an inode, wouldn't be there a point after which like the snapshot inode grows to a certain level that it kind of exceeds the disk memory limit?
Yeah, that means that your snapshot inode must be your double, triple, whatever indirection must be handled enough block for the whole hard disk. So which means that maybe, for example, the block size need to be bigger. So you cannot probably for the larger hard disk, you cannot do 1K block anymore. You probably have to do 4K or even 16K. So the thing is that the configuration has some standard in such that they make sure that when you have inode, that all the pointer up to triple interaction will have enough pointer to handle every single block in your hard disk. That is the given condition, must be true. Otherwise, there is a lot of things won't work in the file system. Yeah, but that's a very good observation. Yeah. Okay, any other question?
Sir, I have a question.
Sure.
What differentiates a snapshot inode from a normal inode?
The main difference is that the real inode, they are real pointer. So in the real inode, that each of this is pointing to some of the disk. So therefore, over here is to represent your disk block number, right? So each of the inode is actually, each of the pointer is pointing to a particular block in the hard disk. And snapshot inode is actually not provide that kind of pointer. It's actually only have two values, either not used or not yet copied. However, the sequence of this pointer correspond to the sequence of the block you try to provide a snapshot. So essentially, I'm saying that the first pointer in the snapshot inode is corresponding to the first block, and the second one could correspond to the second disk block that you're doing snapshot. So and so on and so on. So which means that the last one of the disk is correspond to the last triple interaction inode that you're doing the snapshot. Yeah, that's the main difference. But
Another
the
question,
data
so-
structure is still the same. The data structure is still the same.
The data structure is still the same. How does the system differentiate between these two inodes?
Okay, the system actually doesn't need to differentiate this two inode because snapshot inode is actually being stored as a file. I will actually show you an example. The snapshot inode is it is a file. And the thing is that when you open the file, you actually know that this is the snapshot file. And then you will use the snapshot tool to open it. When you actually open it, you know the representation. In fact, it's not only that. The snapshot idea has the following property. Because anytime any application try to modify the file system, you need to check whether that's actually going to be overwriting some of the block you hasn't overwrite yet, hasn't copied yet. That's copy on write. So essentially in a typical FreeBSD file system, you can take about 20 or 40 snapshots, which means that every time you make a modification to the file, you actually need to check this 20 snapshot to see if any of the file, any of the snapshot need to do a copy. So that's the, so snapshot is actually a kernel support feature. It's not a user level stuff. It's a kernel support level support feature such that whenever you modify any part of your file system, you're going to check all your snapshot inode file to actually see if there is any copy on write need to be done at that time. So essentially we save some time at the time you create snapshot, but you pay a little bit more as you actually actively modify your file system. That's the idea of copy on write. You kind of delay that to a later point.
Professor, a follow-up question.
Okay, go ahead, please.
So if I take a snapshot, does the snapshot inode also get included in the next snapshot?
Yes, that's true. If you take a snapshot, the next snapshot will actually remember the previous snapshot. Yes. And we will see that. We'll actually see some code. Let me actually show you this part. Okay, let me actually tell you how do you make a snapshot. This is typical routine that you actually do a snapshot. All right. So the way you do it is you actually use the mount command. This is the command that you actually take a snapshot. You say mount -u -o you say snapshot. That is a particular option you give to the command mount to actually create a snapshot. So essentially what you did is that you take a snapshot on /usr and you put the snapshot file called /usr snap.noon. Okay, so now you can have a snapshot file. It's actually called snap.noon. I will show you what it looks like. And then you can actually look at the snapshot using md-config, and then you make it a device, and then you mount that particular md0 device into the background. So you can actually access the snapshot using this 2 lines of code to be able to actually look at the snapshot you have. Okay, and after that, of course, you can unmount it, you can remove the snapshot you want. So that's the piece of code that's actually included in the slide. But I want to show you let me actually tell you what I did here. I see that. Okay, so what I did here, you see that I actually make a snapshot. Let me, where did I do the snapshot? Okay, here. You see, I actually do a snapshot. I actually mount /USR on top of that. And then I have a USR snap noon. And look at this file, how big it is. Because this is my whole hard disk, right? So this is what? Logical file size. Because it's not physical. I'm not going to make a copy, but the logical file size is really big. But if you take a look at the DU, the disk usage about this file, it's only about 8 megabyte or 9 megabyte. So it's about like 8 megabyte of a space. I would be able to represent the whole snapshot. So the physical disk size is about less than 10 megabyte, but the logical file size is whatever. It's like 1.6 gigabyte or something like that. I think that was the size I'm actually working on. Okay, so you have, and then if you take another snapshot, then this particular snap.noon will be actually represent. But remember, because this snapshot is actually very small, it's only about like 8 megabyte. So there's not much disk you need to worry about to, in fact, regardless how much you actually snapshot, the size of the snapshot will be more or less the same because it's need to handle the not copy or not yet copy or not used for every single block. That's it. That's what you did. Okay, so now I'm actually going to do something. After this, you can see that after I create the snapshot, I did one thing. Let me see. Okay, I actually, because I take a snapshot /USR, I actually make clean. I'm actually compiling the kernel. I remove all the object code and whatever I do a make a clean. When I do a make clean, now I actually look at the snapshot. Now you look at the middle, the snapshot, the logical size is still about the same. But you look at the physical size is a lot better, a lot bigger. Now it's about 97 megabytes. So from about 9 megabyte to 97 megabyte. Why is that? Because when I do a make a clean, I remove lots of this object file or whatever configuration file. And when you remove it, at the time, I need to do copy on write. I need to actually make a copy so I will be able to recreate the snapshot where you took the snapshot, but before you actually did the make clean. Okay, so that's basically the idea. Okay, so this is actually should conclude my introduction to Snapshot. I think I'm running out of time as well. It's a good time for us to take a break. Any question?
Can I have a question about this figure?
Sure, go ahead.
So you said the left, the first block of the left correspond to the first block of the right?
Right, that's correct.
So the first block of the left is not used.
Mm-hmm.
So should but the yellow block means it's already it's not free.
Right. I probably say it wrong. The color code is probably the yellow is actually free block. The gray block is actually, I mean, it doesn't make sense actually. You know what? No, this is not good because obviously yellow is the block is being used because that's why I need to do copy on write. It's probably the triangle is actually should be moved here. The triangle should represent not yet copy. Yeah.
Oh, that makes sense. Thank you.
You're welcome. Yeah, good catch. Thank you. Okay, any other question? All right, if not, I'm going to see you on Thursday, okay? Let me stop.